The sun is a main sequence star. It is 4.5 billion years old, and it is in this hydrogen burning phase where it is furiously fusing hydrogen into helium at its core, releasing energy, and it creates the sunlight that we appreciate today. But before the sun was a main sequence star, it was a protostar, starting to gather the gas and dust from the surrounding environment, compressing it down into this first proto version of what it would eventually become. Of course, we can't go back in time and look at the sun as it looked 4.5 billion years old. Instead, astronomers have to look at other stars out there in the universe at all the different stages of formation. And we now know of so many seen at different stages, but one of the least understood is the very earliest stage, what's known as the class 0 protostar. This is a star that is less than 100,000 years old, that is nothing more than a growing blob of plasma at the heart of this gas and dust. And eventually, as it continues to contract, continues to compress, it will turn into a star. But the question that a lot of people have is, what are the dynamics involved as material is starting to flow down into the star? Winds are starting to develop, jets are starting to be produced by the protostar that are then blasting material out and creating this interesting balance between inflows and outflows. Now, my guest today is Adam Rubinstein. He is a PhD student at the University of Rochester in the Physics and Astronomy department, and he was part of a team that got access to James Webb to answer this question, to look at various molecules around the heart of various protostars to try to see what kinds of inflows and outflows are going, to really get a sense of star formation for different kinds and masses of stars. But what he found completely derailed his research and led in an entirely new direction, learning a whole bunch of chemistry and getting obsessed about carbon monoxide. Now, we talk a lot about protostars, about Adam's research, but we also spend some time talking about what it's like to work with JWST, the kind of data that you receive and how astronomers work with that data to be able to do the research that they're looking to do. It's not simple, and there's not a lot of roadmaps, and everybody's figuring this out for themselves. So enjoy this fascinating conversation with Adam Rubinstein. Adam, you've looked at a bunch of protostars with James Webb. What is the youngest star that you've looked at so far?
That's actually a tricky question because a lot of times we classify stars not exactly by their age, but by how bright they are, their temperature. Essentially, the stars that I deal with are ones that are the most visibly blocked by dust and gas, so you can't quite see them very easily. Like naked eye, you barely be able to see them. So I would call them the youngest that we know of, but it's a bit of a tricky thing to call it an age. It sort of depends on how you would model it.
But when we think of a star like the sun is 4.5 billion years old and is in the main sequence phase of its life. And we know that there is a phase that comes before main sequence, before you get that full hydrogen burning in the core, which are protostars. And there's a variety of classes of protostars, and several of them come with other names. You know, we have Herbig-Haro objects. Let's approach it this way then, sort of like, you know, what's at the beginning and the end of those early stages of a star's life? You know, when does it go from class 0 to class 1?
I was recently reading some background about this, actually. And it's funny you bring up Herbig-Haro. The original definition for the Herbig-Haro objects were just sources of light that you could see in the visible. But this was in the 1950s, and it was in places like Taurus. And those regions are actually fairly bright and easy to see. So they're not necessarily as old as what we're looking at now. And by old, I mean, say, if you collapsed a whole bunch of gas and dust by gravity, it would take about 10,000 years. On average, like an average region of patch of gas and stuff.
That's surprisingly quick to me.
Yeah, it takes about a mega year, 10 million years for the process to happen. And so when I'm talking about for what I study, it's actually, and what I can study moreover with like the James Webb Space Telescope, it has a lot to do with being able to look at and peer into the most dusty environments, ones that are sort of just starting out. They haven't even begun to get to that million-year age. They're just sort of just starting out.
So, I mean, if you could get close, if you could fly through space and you could approach this object, and when you say just getting started, that means like something is happening. Like it's not just a diffuse cloud of gas and dust that is starting to collapse. There's some knot at the center that is starting to concentrate. And if you could sort of fly through that gas and dust and look around, like what do you think you would see?
So generally, the sort of rough model of what people do, this was in the 60s and 70s, is that you have some clump of gas that is then compressed. And as it compresses, it gets hotter and hotter because as gravity's squishing it further and further together, uh, the gas and the molecules and stuff can gather more energy and take that potential and release light. And that's what you kind of see, especially if you look at longer wavelengths, like at the millimeter, like using a millimeter telescope. But what surrounds that is a whole lot more complicated. The reason I'm being vague is because we're like just starting to like kind of figure it out, and we're just starting to image it. And in those images, you see like you see some similarities, but also some wild differences all over the place. You see a lot of them can have jets of dust and gas being blown away, but they can also have sort of wind skimming off in the background. And it depends on what gas you're looking at and what wavelength you're looking at and all these things. And then on top of that, you also get a disk around the protostar of stuff swirling in and accumulating onto that protostar, thing that'll become a star in like a million years.
But when I think of an object that's kind of similar, like you think about, say, a brown dwarf or even like a Jovian planet, although obviously we're 1/100th the mass with something like Jupiter, you've got an object that is made of the same raw material, gas and dust, with the same rough percentages, but it doesn't have the gravitation to be able to force fusion in the core. And instead it is any heat that is coming off of this object is purely from that gravitational collapse as it's sort of compressing tighter and tighter and giving off heat. And so I'm sort of envisioning a brown dwarf or a very, very big Jupiter surrounded by this disk blasting off these jets that are coming from the poles and then surrounded by this cloak of additional gas and dust that is finding its way down into the heart of this object as it's building. Is that right-ish?
It's tricky to imagine what exactly the like protostar stuff is. I would say that one thing to imagine with a brown dwarf or a Jupiter is that we think of it like a ball of gas. Like, what's a gas? Like air? But really it's hot. It's, like thousands of Kelvin. You can convert it to Fahrenheit or Celsius. It doesn't really matter. And that hot stuff is hot enough that it's a plasma. And plasmas are, like lightning or fire. It's like, you know, it's really hot and burning it. It's dense and it's like tight and bound, but it's like burning hot. So there's sort of like this giant engine at the middle of all of this that is both drawing stuff in and emitting all this UV and such. But
And I mean, there would be a point where, say, you're flying your spacecraft through and it's not really getting any resistance. And then there would be a point where you're flying through, and in fact, this is very dangerous as you're reaching this, as you say, this sort of object that's made of plasma that is rotating rapidly and crackling and sending off radiation. That you would go from that transition from smooth sailing to dangerous object in the middle in that first 10,000 years.
If you have enough gravity, the collapse can happen, like I said, in the astronomical scale, pretty quickly. Like 10,000 years is, for all intents and purposes in astronomy, pretty quick. And so, and the rest of the details about how it acts as a player, that part depends. It depends on how much mass there is. It depends on if it has a partner in crime, a binary. It depends on if it's undergoing, like I was saying with the jet, an outbursting event, which it may not always even be doing. It could just be an episode. It could be like, happens once and then takes a break for a while. Yeah, I mean, I would say, you could just be sitting along in space, you hit a clump, you wait some thousands of years, and then, bam, now you're in some trouble.
Yeah. Okay. And I think, like the question that I get, one of the top questions that I get from tons and tons of people is, when we go from not star, thing that's really hot, that is putting out its heat through purely the contraction and the gravitation friction of the gas, to actually beginning fusion in the core. What is that timeline to go from one to the other?
So that's what I'm saying is like more of the million years.
That's the million years. Okay.
That's a bit of a longer process. And it depends, right, again, if it's a lot of mass, if you can just take 10 suns in one spot and compress it, then it's really fast. Like massive stars, they happen really, really fast. But if it's slow mass, it'll
so if
happen
you've got
slower.
those much larger, more massive versions,
it really depends. Yeah.
Yeah.
But, on average, if I'm talking about like the sun, something like, or like little, couple suns or something, then, million years, let's say that. Million, 10 million, something like that.
And even like a million years astronomically is still bordering on the blink of an eye.
Yeah.
And is this why these objects are relatively difficult to find in those earliest stages, just because there aren't many stars that are going through this process?
Well, if you can find a region where there is active star formation, so I mentioned Taurus earlier, there's a cloud of molecular gas and dust and all that in Taurus. If you find that, like Herbig or Haro did way early on, then you can find a bunch of these signatures. And, at the time, it was still being like, we think about this as like a very star formation. We kind of know this sometimes in or maybe, I don't know. It's like you always see the picture like, oh, you have the gas and it compresses and then you get this disk and you get planets somehow. But, this is all still fairly recent, like 1950s is pretty recent in my opinion. And sorry, to answer your question. Wait, what was the question? Sorry.
Don't worry about it. Oh, you got there.
Yeah.
I mean, you talk about this like fairly recent. I mean, really, it's been the last couple of years. On the one hand, you've got ALMA, which is producing just these incredible images of protoplanetary, like protostellar systems, where you see that dense star at the middle, and you see the dust lanes of this accretion disk surrounding, and you can just imagine their planets gobbling up material and starting to form within that within that accretion disk. And then on the other hand, and this is sort of why I reached out to you, is James Webb has come online, and this is the telescope that lets you see through the gas and the dust to see what's going on internally. So you got time on Webb and you targeted protostars. What were you hoping to see?
That is a wonderful question, because we both had hopes, and also, for my part, I kind of just looked at the data and was like, oh, let me play around a little. Let me see what's in there. So the hopes were that we would see like light from ions, specifically iron and nickel and things that are sort of heavier metals. And when you detect ions in these environments in space, if you have the star, you have jet coming out and winds and stuff, one of the major things that you wonder is sort of how much stuff is coming out and how much stuff is coming in. And by stuff, I mean mass, just a total amount of mass per year. Is the star being built up at a rate of, say, 1/1,000,000th of its total mass per year? Or is it 1/1000,000th? Or is it 1,000th? We don't quite have the answer from that get-go. That's sort of the question, right? As you're asking a lot of times, it sounds like, people might have some kind of notion of this, but it's actually still being worked on. That's the exciting part. And when you look at these heavier metals in these environments, they can take up very low density environments, and we call that a forbidden transition, and are not supposed to happen, as we call them, by traditional speak. Obviously they happen, otherwise we wouldn't see them. And so by seeing that, you can then model the plasma, if you can imagine modeling plasma. And these hot bits of iron and hot bits of nickel and hot bits of argon and neon and all these like ions, you can use that to trace how fast and how dense the gas is moving in this jet or in this wind being blown off, or even being swirled inward to the protostar through accretion. So that was what we were hoping.
Right. And that is interesting, though, because it is a fairly large question in astronomy. When you think about, say, the largest stars, that we know there's a limit to how big a star can get. Like at a certain point, those things balance out, that the amount of material that's coming in and the amount of material that the star is blasting out are the same, and the star can no longer grow. And yet, how do we get big stars early on in the universe? People have questions. So it's, I mean, and these stars are nowhere near those biggest, or maybe they were, I don't know. So
that's the kicker. We had a whole range. We very purposely selected one that was one of the lowest luminosity, one of the lowest mass protostars that we could find in this very early stage, and also one of the ones that was the highest. And by lowest, I mean about 0.1-ish solar luminosities or solar masses, and then also one that was about 10 to the 4 solar luminosities. So just like 10 to the 5 in the range of between these 5 protostars in their luminosity space.
When you say 10 to the 4, 10 to the 5, so you're talking about like a star that's putting out 10,000 times more illumination than the sun does.
Yes, exactly.
That's a big star.
Yeah, and that's a protostar. It's not even finished yet.
It's already putting out more radiation than the sun, and it hasn't even started doing its job yet.
Yeah. So that the ones that are 10 to the 4 just go way faster because they have just so much more mass and energy to just work with, basically. But that said, that's all what we hope to find. And we did sort of find that, but it's a lot trickier than you might think. Because when I looked at the data, I saw that there were lines everywhere. There were these spectra, these spectral signatures and spikes all throughout these spectra that kept repeating. And I wasn't an expert at this at first, but I learned a lot in just a year or two. And I found out that this all has to do with chemistry, and it has to do with molecules, molecular gases, specifically carbon monoxide. So, when you have a fire and you have to have a CO detector, that's the same thing. If you looked in a lab, if you looked in your home and you had a, fire or something, if you looked in space, it's all the same stuff. CO is CO.
Right. And I guess what is creating the carbon monoxide around the star?
So that is a little bit.
I feel like I'm. Are you reliving?
There's always these
sort of a series of questions that you had as you were talking to me.
Yes, actually, a lot of these questions are like sort of my past year of reminiscing. Like, oh yeah, what caused that?
I remember.
Do we know the answer?
Right. I remember when we looked at that and wondered to ourselves, where's this coming from?
Because see, it always feels like you know the answer, but so in this specific case. The common theory would be like you look at these, the things you said with ALMA, those would be considered class 2. So they've sort of gone through they haven't fully gone through their million years, but they're pretty much at the end stages of that. And when they get to that point, you can see nice layers through the disk, and you can even see, when you look at them in the past works, you can see the carbon monoxide is still there in these layers on the surface of the disk. And the carbon monoxide itself, the kicker is that it doesn't actually tell you like everything about the system. It just traces this little surface layer, and it's just very, very sensitive and very, very easy, very, very able to survive in these environments, in these very, very hot environments. Like it can get up to 1,000 Kelvin easily at the densities of in that environment and still be just fine. So we use that a lot to do what's called tracing or probing that environment, or it's like a proxy. So we know how much CO there is. We can literally count using physics how many CO molecules there are, and then turn that into how much hydrogen there is in that little itty bitty area near the disk, right there. So that's to say we had a kind of preconception of, oh yeah, the CO has to be in this little area. Except when you looked at data from Spitzer of the younger stars, there was another preconception, which was that the CO happens to be along the jets. It's a lot more excited. And these look at two different types of transitions or energy levels from the CO molecules. So you can count CO in all these different ways. Okay, enter JWST. You get the whole spectrum from about 4.6 to about 5.2 microns, and it consists of 200 spectral lines. In the past, we'd only get, a few here, a few there. You get 200, which is a lot more information. And so you can use that to then look at, what are the temperature of all of these types of gases in this region, and what is the amount of mass in all this region, and you find that does it match the environment that it came from, basically. So that was sort of the original question you were asking, right? Where does it come from? The natural idea in astronomy would be, okay, well, you have a cloud, it's a mixture of stuff, you compress the mixture of stuff, it stays about the same. It has the same mixture of gases. So same amount of hydrogen, the same amount of carbon monoxide, same amount of neon, iron, so on and so forth, right? Ultimately, when we get to the solar system, though, it has a slightly different composition. The Earth is a collection of all this compressed onto its own self. It has water, and has a lot of water compared to surroundings. When you look at the carbon monoxide, for me, the carbon monoxide itself didn't necessarily seem different from its surroundings, but what you can tell is the isotopes. So there's isotopes of these chemicals, and isotopes means that they sometimes have an extra neutron, so they're slightly heavier, sort of like deuterium. And the weirder part was that I didn't detect any isotopes. When you look in the environment and all the surroundings, you always see isotopes everywhere, especially in the older protostars. But in this case, we didn't. And we're still trying to figure out why. But one of the key things about that is that that's usually implying a lot of destruction, selectively destroying that CO. And the way you do that is pretty much just through UV. You either need to take out some of the CO or you need to destroy it. And so, sorry if I'm going I don't know.
No. So I just want to sort of see if I'm following your trail here.
Picture,
So I think about, say, carbon 14 versus carbon 12 here on Earth. And we know that carbon 14 molecules are being created as radiation, as space is hitting molecules in the atmosphere or from the sun, and is juicing them up and then they decay. And you can tell, a tree brought in the carbon 14 and then it decayed, and you can measure the ratio of the carbon 14 to the carbon 12. And if you don't see the isotopes, then it feels like things aren't being replenished, that you're not getting a fresh source of the carbon. Like if it was a fresh source, you'd be seeing this mix of the isotopes, and then they're decaying to the next level, right? Mm-hmm. Is sort of my impression.
So I can answer this so now we have to back a bit more out. So if you're wondering where this reservoir of material is streaming in from, there's this sort of envelope covering up all this stuff. And from that, we can draw gas into the disk. But not only that, we also have ices that are frozen, say at 100 Kelvin, much, much colder than room temperature. Like, what's that? Like a third of room temperature or something. So pretty chilly. Like dry ice. And we also detect ices in these systems. There's a sort of layer of ices surrounding all of this material. And that consists of carbon monoxide, carbon dioxide. It also consists of a whole bunch of other long chemical names that I won't name. But that's sort of our resource for getting stuff from the outsides in.
And I know there's been a lot of really interesting research seeing, say, the transportation of these ice-rich particles coming down close to the star itself, and this could very well be a pretty good explanation for how Earth got its water, that there is this transport mechanism that's going on and bringing this material down into the center of the nebula. Yeah,
so this is sort of like the earliest part of that enrichment process of bringing stuff in to the insides. And then, but the weirder part is, in my stage, which is so young, it's brought in there, like carbon monoxide, for example. And let's just forget that carbon and oxygen are also important. Oxygen helps with water, and carbon helps with life.
We need both of those.
Yeah. But when you bring it in to the surface region little area that I'm looking at, it appears that it's getting blasted by UV, but the actual standard CO carbon monoxide that I look at is surviving. What gets destroyed, or at least I don't see, it's a lack of a presence. So this adds to a lot of our confusion. But we don't detect the isotopes. So, and that can either be that the isotopes are getting refrozen into the disk, or that the isotopes are getting blasted by this radiation from the star, from the protostar.
Selectively.
selective.
Right. I mean, I can see how you are realizing that you stumbled into a completely different set of questions than the ones that you were
Exactly. It's a
hoping to answer.
complete rabbit hole.
Right. You were like, I wonder how, as stars have infalling and outflowing material and how that balances their star formation rate. And what you found was that molecules like carbon monoxide are being drawn in close to the interstellar environment and are surviving for longer than they should. And this could help explain planet formation, life, right?
But this is just one molecule. Of course, we need to look at all of them. And carbon monoxide, I'm told, is the easiest one. Easiest being, it's the simplest, though. And yeah, I just liked the fact that, honestly, it just popped up all over the data. And you couldn't ignore it, basically, is how I would put it. If you popped open the spectra or looked in the plots that I had, it was everywhere. So that was one really interesting thing.
So it sounds to me like the answer is more time, on which I'm sure is the answer that every astronomer comes up
Yeah,
with.
it's
Is,
always the answer. Yes.
if I just had more time, with more time, more data, better spectral lines, more molecules should start to pop out of the noise.
Yeah.
What would you be hoping to see with more time, 10 times more time on Webb to image those stars again?
So serendipitously, the last cycle, which was last year, every year we get a new cycle. And throughout the year, the JWST observes that based on a whole slew of proposals that get submitted. And my group submitted one of the larger proposals. There's different sizes. You have large, medium, small. And that's how much time you're being awarded. And one of our larger proposals actually got accepted. So there's going to be a lot more of these types of protostars being observed. And what we would hopefully expect is to see either something to do with either the background or the environment that it's in causing these differences in what types of protostars we ultimately get out, and what types of predictions for how many stars we get out or how many planets we get out or something like that. And alternatively, whether it doesn't have much to do with the environment and there's no correlation you can form out of that, and it's just you form a star there and the star sort of dominates the system, or somewhere in the middle, probably somewhere in the middle. But if you have an OB type star, a very, very hot, massive star on the main sequence, and it's blasting with stellar winds and it goes supernova, probably that'll affect things a little. But we're kind of seeing this whole environment very dynamically, and it's happening all at once. And so you're just kind of taking snapshots of all these different parts along this nebula and seeing, all right, here's one, like I said earlier, here's one protostar, another, and see, all right, are there any differences in them? Does some of this have more water as ice? Do one of these protostars have more water as a liquid?
I'd be interested to know what it was like with your journey in receiving the data in the first place and working with it, because we're so much at the beginning of people learning how to work with JWST. What was it like to sort of get your data and then try to answer because it sounds like you realized that you now had new questions that you had never planned to ask before. You didn't quite get the answers you were hoping for. Do you think it's in the data still, or do you need to do more analysis, as you say?
I am very much an observational person. So I like observations. I like, getting pictures and spectra and then saying, yeah, I think we can get something out of this. I've had many a challenge, with data sets. For example, images that were taken while the telescope wasn't tracking any background stars. That was one of my first data sets that I had to contend with using the Hubble. And, I always think, yeah, we can always try. Why not? So I think these the answers are still in some of the these first 5 protostars, this sort of first draft of what we're looking at. But that's we're still working on that. And hopefully when we get this next proposal, we'll get even more data to then bolster those points. But that's all one part of that question. The other question was, how does it look like when we get the data, right? And basically what happens is you take your telescope, you point it somewhere, you go through a few double checkings, like, is this really where you want to point it? And it's like, yes, this is where we really want to point it. And then they're like, are you sure? And then we're like, we do our homework, and then we're like, oh, actually, maybe change it a little bit. We talk a little bit and make sure we're really sure that, this is a pretty expensive machine and we want to point it. We don't want to waste any time, And okay, we're really sure we want to point it to this one protostar. Okay, now that we've done that, you can take the data with a few different instruments. So there's one that is the near-infrared one that I focused a lot on, called NearSpec, and there's another one called MIRI. NearSpec covers about 3 to 5 microns, so it's a near-infrared instrument. And then MIRI is the mid-infrared, and it covers about 5-ish microns all the way to like almost 30 microns. So it's probing a lot longer wavelengths. The trade-offs are that in the near-infrared, you can get a lot better images. They're a lot, the pixels, the individual pixels on the images are a lot finer in their grid than in the mid-infrared. The other trade-off is that different molecules show up, or different elements in general, and signatures show up between the two instruments. So if you have a range from 3 to 20 microns, you get a whole lot more stuff. That's why I said it's probably somewhere in there. But if you only have 3 to 5 microns, you also get a lot of stuff, but it's mostly carbon monoxide in my case. So, okay, you've made the whole plan. It looks at this square patch, and we do one data set, we do another data set, it gets shot down to Earth, NASA processes it and says, okay, you're good to go, here's your data products. It's raw data, and raw data looks like a bunch of, zeros and ones and a lot of messy. Have you looked at raw data before? It's just a giant mess of like
FITS files, things like that.
Yeah, it's wild. But okay, you take that and you say, I want to look at one of these pretty pictures we see, like the Orion Nebula, or, like the Tarantula Nebula, stuff like that. And to get to that point, that's where I come in. And first with my team, we have to make sure all of these different scans of the region, sometimes you take 1, 2, 3, 4, or like dithers, they're called, I think. They're all aligned. Okay, so you go through the process, you make sure you check each square panel and all the pixels are exactly aligned in their little overlaps. After you do that whole alignment procedure, which I think a lot of people who are like ground-based observers might be used to, then you have to go and do masking, another step that I think a lot of ground people with just regular telescopes and cameras are used to, where you go and check to make sure there's no what we call artifacts. And the artifacts come up because there's dust, somewhere like smudging or something. Probably not smudging, you could probably wipe it off or something, or because there's a star there and it's really, really bright and it causes these spiky diffractions. Okay, so you get rid of the spikes from the diffraction, get rid of some smudges here and there, and now you're left with a clean-ish image. It's not just one image, though, because this instrument is special. It's a hyperspectral imaging, or it's a spectral cube. So that means that for every single pixel, you get a fully resolved spectrum. So you get all of the data about the composition and about how bright the stuff is, as well as pictures for every single one of those elements and molecules.
That's
And so,
crazy.
yeah, it's a lot of data.
That you're getting the spectra on every pixel, which I guess is super important because you're trying to see what are the chemicals here, what are the chemicals there, what are the chemicals there.
Does it
but the
differ
fact
in
that you're
this
getting
jet?
this,
Does it differ exactly?
yeah. But I had no idea that astronomers were getting a full spectra on every single pixel of an image that they get back from JWST. Is that different from other telescopes, or is that?
So there were other telescopes that do this, but they're primarily ground-based because the ground-based instrumentation usually is prototyped a lot faster than stuff we can send into space, because we want to make sure whatever we send in space is top-notch, For example, the Spitzer Space Telescope and the Hubble Space Telescope have broader band filters. So they capture one wavelength, like 1 micron or 3 microns, but with a much broader spectral filter. And so that means that it collects a lot more light from different sources, or different elements or different processes. While this is able to narrow in on each and every single one, which is crazy.
Wow. Okay. Well, so I interrupted you. You were talking about you get all the spectra.
Yeah. And then that's the part that I had to figure out. Nobody had instructions for that. So I just had to figure it out. Yeah.
Right.
And so I had to look at, every possible numerical technique. I'm not going to get into all of it. But the point was basically the reason this all came up in the first place was we wanted to get at all these different ions like iron and hydrogen and nickel, but there were these CO lines, you might say, in the way. They all overlapped. And ironically, now we're doing the reverse. Now we decided, all right, well, can you make an image and a spectral measurement of every single one of those 200 lines for me, Adam, and get this out so I don't have to deal with it? And I'm like, yeah, sure, I'd be happy to. So, there's sort of a handshake, a win-win on this. Someone else wants to work a lot with this, ice, which is this really broad absorption. And I want to look at every single one of those spikes. And so I go ahead and I take out every single one of those spikes at every single pixel. And that gives me how much CO there is at every single pixel. And what's even better is this, some of the molecules like CO or like water, sometimes it comes up hot, and so it spikes up. And sometimes, it's very hot, but sometimes it's colder and it goes down. So you have to figure out ways to sort of quickly get out, okay, is it more of an emissive process or an absorbing process? Is it colder or hotter? And you got to do that at every single pixel because it varies all over the place.
Yeah, that's amazing. But it's funny though, when you're at this process now, are you still interested in the answer to your original question? How quickly do stars form at which points in their evolution? Or are you now, you had to go and learn a whole bunch of new chemistry just to understand the interactions of carbon monoxide and what role it plays in early star formation? Where do you think it goes next? Do you try to get a better answer to the original question that you had with just more data? Or do you start to really learn all of the requisites to chase down this new question that you've gained, which is, I think has all kinds of impacts in just literally the formation of planets and even the origins of life itself?
Yeah, so I think the answer to that is you try to do everything, which is hard.
That sounds like my answer too. Yeah. Yes.
Yeah,
yes.
because, all the questions can be interesting. And also, you need to be able to, like you kind of do, look at the sort of grander scale of things and think, all right, well, how do all these different processes connect? And so you need to kind of be able to look at both problems at once admittedly, I like to focus a lot more on like one problem. So I will probably work on like, just the carbon monoxide for 1 or 2 years, but then I'm like, all right, I've done that. I'm going to let everybody else try a crack at it. Now I'm going to work on the ions, So I'll kind of switch every year or two. Because I think, it's more fun to sort of trade off ideas and get different inputs on how that research works. But yeah, I don't think you're locked into one thing really.
Yeah, yeah. But it is really interesting to sort of hear what it was like personally to be at the receiving end of the torrent of data, and the fact that there weren't a lot of roadmaps that you could follow. That a lot of this, and this is probably the same experience. The exoplanetary hunters, the people who are observing these galaxies at the beginning of the universe, each one of them is going, well, what do I do with this? There's no guide yet, and I have to learn. I have to figure out how to get the most out of this to get the questions answered that I need. And we're still a few years away from the best practices starting to form, just because this telescope is beyond anything that anybody's ever had access to in the history of science. Adam, what are you obsessed with right now?
I'll just also add, NASA and the help desks, they're great people. I'll just say that. But just to give credit
I can
where
just
it's
imagine.
due.
Hello, Adam. Yes. How can we help you today?
But and my team and everyone. But what I'm obsessed with, like scientifically,
or
um,
or not, but yeah.
um, I think one thing that's sort of piqued my curiosity recently is the fact that, well, when I look at other papers in other fields, they do somewhat similar techniques almost. Like if you look at remote sensing projects, or if you look at people studying the solar system, they also use hyperspectral data, or they also look at carbon monoxide of other planets. And so one thing that sort of piqued my curiosity, which I can't, just dive into, I'm a scientist, I have to take my time and study the field and kind of talk with people. But it's like, how do other people look at these things? Like, do other people look at like comet ices and say, oh yeah, obviously it has this composition? Or do they look at remote sensing images of Mars and say, oh yeah, we can look at the hyperspectral images and see, bits of iron and bits of nickel and stuff on Mars? And how do those techniques sort of similar, like relate, or how do they differ and things like that? So that's one half. And then the other half that piques my interest, there's a lot of interest always, is how do the two instruments that I was using, NearSpec and MIRI, or how do two instruments like a ground-based telescope and JWST, how do they work together? Because I think that's sort of, we already have a lot of data, but the next natural step is, okay, well, now can we combine them and get these measurements that we can take at the same time and tell different things? Do they agree? Do they disagree? Can we use them to test out, next generation of, of whatever scientific theories we have, or so on?
Yeah. I mean, we always say that astronomy is sort of like the only science that you can't perform experiments. All you can do is observe.
Yes. Yes.
But if you can observe with those two instruments that are seeing different parts of the wavelength, but mildly overlapping, then it could very well be that you get some features that you see in the one instrument and then other features that you see in the other instrument, that it allows you to answer even more questions than you could before. I don't know. It's kind of like how you can look with your eyes, right? You look with one eye, you look with the other eye, and you can see okay, but it's when you look with both at the same time that for some magical reason you can perceive much better when you're using both eyes at the same time. And I can sort of imagine that coming into it, like on the one hand, it feels like a hassle because you have to normalize the data between these two instruments, but at the same time, the advantage is when they're not normal, when they're behaving differently from one another, there's like some insights in those in the diff.
Yeah. And then you can use that to do more experiments and so on and so on.
Right. Yeah.
It goes
Yeah. The
on
cycle
forever.
continues. Yeah.
Yes.
Well, Adam, it was an absolute pleasure to talk to you. Thank you so much. And hopefully this will give me a much better answer for when people ask me, like, when does a star turn on? And also,
Sort of answer.
sort of. It sounds like it's complicated, but I do also love that you have sort of gone and rabbit holed into a completely different area than what you had originally planned. And it sounds like it's going to be very, like, very impactful. Like, you sort of stumbled accidentally into some of the most important questions that people are asking about stars and planets and so on. So it's pretty interesting work. Thank you for your time. I hope you enjoyed that conversation with Adam Rubinstein. Now, I'm going to talk more about some of my thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Barry Lake Roofing, David Gilton and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Krasaki, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. One of the things that's really interesting to me, and we didn't talk about this in this interview, but when there are various astronomers who are receiving data from JWST, and this data is embargoed, right? This science team has access to this research for 12 months before it's widely available to the rest of astronomers. And so they've got this time to be able to work with this data. But there are no roadmaps that, when you get those data, you've got your various filter information from the different instruments on board Webb. And as we talked about this, like, you've got the spectra from every single pixel that is just like so much material and information. And yet this, in many cases, people are working for this for the first time and they're having to learn how to do it. And I think while the embargo is good to give people the time to do science that's well thought out, maybe it would have been great to have a couple of years where there was no embargoes, that everybody's sort of working with the data and trying to come up with some best practices to be able to figure out how to work with this, but then they can use those to sort of streamline their process later on. Because my guess is that each team that's getting access is having to come up with their own suite of tools, their own pipeline to be able to deal with this. So it's a sort of an interesting and tricky problem that maybe more communication, more sharing would be useful early on in the process. But, here we are. Anyway, hope you enjoyed the conversation, and we'll see you next time.